Industry uses steel, which comes in a variety of shapes and sizes. This closed-die hot press is forging crankshafts for the motor industry. Each piece of steel has been cut from a bar, and those steel bars began life as scrap. You can't just take this scrap metal, melt it down, and turn it into steel bars. Industry demands bars of a certain shape and dimension, and a specific metallurgical composition. To achieve all that, you have to subject the steel to very precise and expensive processing. The process is known as rolling. By rolling steel, you can produce rods, bars, plate, and sheet. At its simplest, rolling is the squeezing of steel between pairs of specially shaped solid rotating cylinders. They're called rolls. Rolling calls for steel with good malleability, and the hotter the metal, the more malleable it is. First of all, the scrap has to be melted down. And that's done in an electric arc furnace. At this stage, certain additives can be mixed with the metal to improve its properties. From the melting furnace, the liquid steel is taken to be poured or teamed into molds. Each mold holds 6 tons of steel. When the metal is cool enough, the mold can be removed, leaving a solid hot ingot behind. These are taken straight away to the rolling mill. When they get there, they won't be hot enough to be rolled immediately. First of all, they have to be heated to an even temperature of 1300 degrees centigrade from the surface of the ingot right through to the core. The ingots are heated in what's called a soaking pit. Depending on the quality of the steel and the size of the ingot, they may remain in the pit for up to 8 hours. The pits provide a useful buffer period for the ingots during their journey from the furnaces to the rolling mills. What's wanted is a steady supply of steel at the correct rolling temperature. It can waste both time and money if the whole rolling mill has to stand around waiting for ingots to reach the right temperature. During heating, the ingot acquires a surface scale. When this flakes off in handling and rolling, it carries with it some of the defects which could mar the surface of the ingot. The interior of the ingot has an uneven structure. When it's poured, the hot liquid metal touches the cold surface of the mold. The sudden cooling effect creates small crystals at the surface of the ingot. As you move towards the center of the ingot, this cooling effect is not so marked, and the formation of the nuclei of each crystal is retarded, and the crystals get much larger. So, in a really large ingot, the crystal size can vary a great deal from the surface to the core of the metal. Rolling has a twofold purpose. It gives the steel its desired shape, but it also imparts a homogeneous quality to the metal, improving its tensile strength and toughness. When it's cast, the ingot has a coarse, crystalline structure. The squeezing of the rolls elongates the crystals and aligns them in the direction of the rolling. But since the metal is hot, fine equiaxed crystals are formed at the grain boundaries due to recrystallization. Under the great heat, these grow into larger crystals. As the ingot is passed through the rolls, the crystal size becomes more uniform. As a result of rolling, the crystal structure of the steel becomes more reliable and more predictable. This is the cogging mill. It's a single-stand, two-high reversing mill. The whole of the rolling unit is known as a stand. This stand uses two rolls, and that's why it's called two-high. It's known as a reversing mill because the ingot passes forwards and backwards during rolling. The mills have very powerful motors capable of changing from forward to reverse in less than 2 seconds. Each pass through the water-cooled rolls can reduce the thickness of the ingot by 2 inches, squeezing it longer and longer. The man who controls the rolls, the cogger, sits in a reinforced glass cabin, known from its commanding position as a pulpit. The pulpit straddles the roller table and gives the cogger an excellent view of the whole operation. Even when the ingot disappears into the rolls, closed-circuit television shows him what's happening on the other side. Getting the rolling temperature right is very important. If the metal's too hot, the steel becomes burnt and less malleable. The burning, due to excessive oxidation of the surface of the steel, leads to grain boundary embrittlement, a condition which can lead to the cracking of the metal as it goes through the rolls. If the temperature is too low, the rolls themselves could be fractured by the extra force needed to roll the metal. To reduce these ingots from 26 inches square to roughly 7 inches square could involve passing them back and forth through the rolls up to 15 times. On each pass, the rolls can exert a force of up to 1,000 tons. After being rolled to size, the ingot, now known technically as a bloom, travels down the roller table to the scaffer. Here, any remaining surface defects are removed by exposing it to an oxypropane flame. Next, the bloom is made even thinner. This time it's passed through a set of water-cooled vertical rolls. After this, it goes through a set of water-cooled horizontal rolls. Before entering the finishing stands, the front of the bloom is cut off, leaving the end true and square. The cropped hot bloom normally goes directly into the billet mill stands. This one is known as a 4-in-line continuous 2-high mill. Each of these rolling operations imparts a more definite grain flow to the material, as well as giving the billet its final desired dimensions. 7 inches square now, it's grown to some 40 feet in length. At this stage, it's cut into more manageable lengths by a flying shear. The blades move forward with the bloom as they cut, then return ready for the next cut. The trimmed lengths are stamped with the cast number and the relevant identification marks before being passed down a roller table to a cooling bed. These beds slide the billets, as they're known at this stage, slowly forward as they cool. The billets are formed into various shapes, round, hexagonal, square, and flat. In this, one of the most modern computer-controlled rolling mills in the world. The billets are loaded into a furnace fired either by gas or oil. The billets are walked through the furnace and discharged at the other end straight into the rolling mill. The mill is made up of 18 independent stands in a line which progresses from roughing to intermediate and finally to the finishing groups. From the moment the billets leave the furnace, speed is essential. As the bar moves down the mill, it grows thinner and longer. The movement is computer-controlled and assisted with closed-circuit television. To keep the end of the bar straight and true, intermediate nose cropping is carried out by sets of flying shears stationed after stands 8 and 12. By the time the bar reaches the final stand, it can be moving at up to 40 miles an hour. After cropping into its final length, the bar is checked to see that it has the right dimensions, and it's then passed through a water quench. This helps to prevent the formation of scale, and it also produces a better surface finish. Finally, the bars move to a cooling bed. The chemicals added to steel to change its properties can make the rolling process more difficult. Sulfur, for instance, can set up what's called low transverse ductility. This may well cause the ends of the bar to split open. When that happens, they may catch a guide on the line and erupt into a spectacular snaking frenzy known to the cool-minded men in the mill as a cobble. And here is a right old cobble. No wonder everyone in the area wears heavy protective clothing all the time. Come near a cobble like this unprotected, and you'd be in trouble. It's essential to remove this tangled 2-ton bar from the rolls as quickly as possible. The longer it's left, the greater the damage it could do to the installation. The mill is so expertly designed, the men so skilled, that within a few minutes of a cobble arising, the mill is back to normal. If you have to produce bars like these, primary rolling of the original ingot is essential. But in the making of sheet steel, there's a new method which eliminates the initial making of the ingot and primary rolling. The process is called continuous casting. Molten metal is poured into an open mold from which the slab issues. This machine can cast up to 14,000 tons of liquid steel a week. The steel is poured into the top of the long water-cooled mold, which is curved to help save space in the works. From the open bottom of the mold emerges a solid hot ribbon of metal which can be cut into suitable sized slabs for rolling. They can be up to 6 feet wide and from 6 inches to 12 inches thick. The slabs are allowed to cool and then stored in a stockyard until they're needed. When they're acquired, they're heated to 1300 degrees centigrade, ready for rolling. The rolling is done in the hot strip mill over half a mile in length. The slabs are passed, first of all, through 2 sets of descaling rolls, which remove most of the surface scale. Next, they go to a 4-high single-stand reversing roughing mill. It's called 4-high because for each of the water-cooled work rolls, there's a large backup roll which lends strength and pressure to the operation. All the time, the slab is getting thinner and longer. Both here and in the finishing stands, jets of high-pressure water are directed onto the surface of the metal to clear it of any remaining scale. It's very important that all the scale is cleaned off before the hot metal enters the finishing stands. Otherwise, it will penetrate the surface of the finished material and affect both the final properties and the surface finish of the strip steel. When the material has been rolled from its initial 9 inches down to anything between 2 inches and 1/10 of an inch thick, it's known as plate. Plate can be up to 12 feet wide. From the roughing mill, it's on to the finishing mill, where the thickness is further reduced and the length correspondingly increased. In order to meet the high standards of flatness required across the width of the sheet steel, all 6 stands in the finishing train are 4-high. These large backup rolls are needed to limit the bowing of the smaller work rolls under the heavy working strain. Because the strip is continuous, and it's usually in all the stands at once, the entry speed of a particular set of rolls must exactly match the speed of the steel as it reaches it. If it doesn't, the tension of the strip metal between the stands can lead to unacceptable variations in the thickness and the width of the finished steel. It can occasionally lead to breakage of the strip. So getting the tension right between the mill stands is critically important. From the finishing stands, the strip emerges at a roaring 40 miles an hour down a long run-out table over which multiple water jets are playing. The temperature of the strip has to be nearly halved from its 1100 degrees centigrade before it can be coiled. In its lighter gauges, the strip steel would present insuperable handling problems unless it could be coiled as continuously as it arrives. After coiling and cooling, it can be dispatched, but it's still quite soft. If the steel is going to be used to press parts for cars, for example, it'll need to be toughened and have its surface made hard. Cold reduction, or cold rolling as it's known, will achieve this effect and, incidentally, make the sheet even thinner. Before this can be done, any surface scale and rust which has accumulated while the steel has been stored will have to be removed. This is done by a process known as pickling. Again, it's a continuous operation. The strip is uncoiled, and to avoid having to thread each coil separately through the line, the end of one coil is welded onto the front of the next. The strip is then passed through a series of hydrochloric acid baths. After the acid, it's washed in water tanks and finally passed through hot air dryers. The strip is then coated with oil to protect it before being rewound into coils. The bright, clean coils, protected against corrosion, go next to the cold rolling mill, where they're reduced to the required thickness. Typical is this 5-stand mill, which passes the coil through a series of rolls in tandem. Each set of rolls is mounted in a 4-high configuration. In cold rolling, the squeezing action of the rolls not only thins the sheet, but also alters its structure. It imposes on the strip an elongated grain structure aligned in the direction of rolling. Because no heat is involved, recrystallization and grain growth don't take place. The reduction in thickness is helped by maintaining the tension in the strip between each of the stands in the mill. In this way, the thickness of the material can be reduced to a few thousandths of an inch. One disadvantage is that the strip steel does become work-hardened by this method of cold rolling. Some cold-rolled steels tend to crack if they're used straight away. This can be prevented by annealing. The coils are heated in an inert gas atmosphere. The absence of oxygen prevents scale appearing. The coils are kept at 700 degrees centigrade for 72 hours, and then allowed to cool slowly in their protective blanket of inert gas. To meet their final specification, the coils are subjected to temper rolling. They're passed cold through a single-stand 4-high temper mill, where a small reduction in thickness, not more than 4%, takes place. This operation also removes any residual undulations and induces a controlled amount of hardness or temper into the surface skin of the cold rolled strip, which has become soft after the annealing process. Cold rolling is ideal where the material isn't thick enough to retain its heat and where a first-class surface finish and exceptional dimensional accuracy is demanded. Hot rolling is reserved for the breaking down of large steel ingots into sections, plate, strip and bar of various shapes and sizes. Some of these techniques date from the 17th century, and they haven't changed much since Edwardian times. Others are new, exciting, and offer tremendous opportunities for the future.